This example comes out of section 2.1, first principle. The root function, radical function f of x equals the square root of x plus 4. We're asked to find the derivative of that and state the domains of the original and of the derivative. Now, finding the derivative by first principles here in 2.1 means going all the way back to this limit business. Later on you'll find that there are some nicer ways of doing that that are much shorter, but here we are. We've got our equation. So limit as h goes to 0 of the square root of x plus h plus 4 minus the square root of x plus 4 divided by h. At this point we need to rationalize because we can't just put in h as 0 there, so we multiply by the conjugate of the numerator here, x plus h plus 4 plus square root of x plus 8 x plus 4 on the top and on the bottom, square root of x plus h plus 4 plus square root of x plus 4. What that does for me is changes what this looks like without changing its value. I'm going to have x plus h plus 4 minus x plus 4, all that over h times the square root business here of x plus h plus 4 plus square root of x plus 4. Denominator looks awful, but the numerator looks quite nice if you go one step further and realize that x minus x is 0, 4 minus 4 is 0, and all I have left here is an h. And on the bottom I have an h that's factored out as well, so we're going to be able to cancel out those h's and be left with the limit as h goes to 0 of 1 over the square root of x plus h plus 4 plus the square root of x plus 4. H can now actually go to 0, and we have 1 over square root of x plus 4 plus the square root of x plus 4, which more simply put is 2 times the square root of x plus 4 in the denominator. That is the derivative of this function. Now for stating the domains of these two things, the original f of x equals the square root of x plus 4 has a domain that x plus 4 needs to be greater or equal to 0, so x needs to be greater or equal to negative 4. If you look at that picture, 1, 2, 3, 4 to the left, and you have a curve that looks like that. The derivative has the equation of 1 over 2 times the square root of x plus 4. The square root term there is the same, so x still needs to be greater or equal to negative 4, but since it's in the denominator, it can't be equal to 0, and so you have just that x has to be greater than negative 4. And this makes sense given that you can find the slope of the tangent to anywhere on that curve, but this endpoint is not differentiable. In other words, you can never draw a tangent line if the graph ends at a certain spot. So in this case, this graph ends at x equals negative 4. And so what you'll find is that the domain of the derivative is always a subset of the domain of the original function, meaning that it might be the same or it's less. You'll never have a domain of the derivative that's more inclusive than the domain of the original, because that wouldn't make any sense. You couldn't find slopes of tangent lines on points when there isn't even a point on the original function, if you think about it that way. The last thing I wanted to mention in this are some differences in notation. I've been using the y equals f of x and y equals f prime x notation, and that is pretty common. You'll also see this unusual notation that equals dy by dx, and you'll see that quite a bit actually, so we should make sure it's called Leibniz notation, named after one of the the fathers of calculus. So in an earlier example we did y equals x squared, and we said that the derivative of that was 2x. You could also say that if f of x equals x squared, that the derivative this way is 2x. You'll even also find occasionally they'll use y prime, like they'll say if y equals x squared, y prime equals 2x. And these things all have the exact same meaning, so don't get confused by them. There's nothing really different about them. The last very strange notation is to say if I've got f of x equals something, f of x equals y equals f of x, the derivative of f of x with respect to x is kind of like this is saying the same thing as dy by dx, since y equals f of x. So kind of just either prime notation or Leibniz notation, to different ways of saying the same thing. Hopefully this dy by dx notation reminds you in some small way of delta y over delta x, which we talked about when we talked about slopes, and that's, I think, the intention of it, or where it comes from.